Welcome to Kognito Key. It is fantastic to have you here. Today, we're jumping straight into a super focused and honestly completely fascinating exploration of electrical transformer mechanics. I mean, if you've ever wondered how engineers manage to squeeze every last drop of efficiency out of our power systems without wasting energy, well, you're in exactly the right place. We're looking specifically at maximum transformer efficiency and the exact mathematical logic that makes it all possible. Let's get right into it. So let's set the stage with a big question. At what exact mathematical point does a transformer actually reach its peak efficiency? We all know transformers are the absolute backbone of the grid, stepping voltage up and down. But they aren't perfect, right? They lose some energy as heat along the way. So how do we operate them in that perfect sweet spot where energy waste drops to a minimum? Well, today, we are going to logically deduce the answer to that exact question, step by step. Before we solve that, let's quickly ground ourselves. Transformer efficiency, denoted by the Greek symbol eta, is essentially just the ratio of useful output power to input power. Both of these are measured in watts or kilowatts. Simply put, it's telling us how much of the electrical power you pump into the transformer actually makes it out the other side as useful energy. Obviously, the closer that ratio is to a perfect one-to-one, the better the transformer is performing. Now, to really grasp efficiency, we have to talk about where that power gets lost. We're looking at two primary types of energy waste here. First up, we've got iron losses, which we call PI. This includes hysteresis and eddy current losses, but the absolute key thing to remember is that these are constant. Whether the transformer is powering a whole block or literally nothing at all, iron losses stay exactly the same just because the magnetic core is energized. Second, we have copper losses, or PC. At full load, this is the secondary current squared times the equivalent resistance. The big difference here? Copper losses are variable. They naturally ramp up as the wire heats up from carrying heavier electrical loads. Because those copper losses are constantly fluctuating, like how power demand spikes in the evening and drops at midnight, we need a clean mathematical way to represent how much work the transformer is doing at any given moment. Enter our variable, x. We use x to represent the fraction of the full load. So if your transformer is running at exactly half of its rated capacity, x is just 0.5. This simple little variable is literally the key to unlocking our maximum efficiency condition. Okay, so let's follow the math. Step 1. We establish the efficiency equation based on the load current. Since terminal voltage is pretty much constant, efficiency really hinges on that load current. Step 2. To maximize the efficiency ratio, we need to find the absolute lowest point of energy waste. If you run a bit of calculus on this, specifically by minimizing the denominator where our variable losses live, we arrive at a major theoretical breakthrough. Step 3. Maximum efficiency happens precisely when those variable copper losses perfectly equal the constant iron losses. And that brings us to the climax of our derivation. X squared times PC equals PI. Think about it like this. Our variable copper loss is dictated by the fraction of the load squared, that is the x squared part, multiplied by the full load copper loss, PC. When that specific value balances out and perfectly matches our completely constant iron loss, PI, boom, your transformer has hit absolute peak efficiency. So the million-dollar question is, what exact fraction of the full load creates that perfect balance? By using some basic algebra to isolate our variable x, we get a beautifully straightforward result. X simply equals the square root of PI divided by PC. This mathematically proves the exact fraction of the load you need to hit maximum efficiency. If you know your constant iron loss and your full load copper loss, you instantly know your sweet spot. No guesswork needed. Which brings us to this final, incredibly elegant formula. If you want to calculate the exact power output where your transformer performs at its absolute best, you just take your full load kVA and multiply it by that optimal fraction we just derived, the square root of iron loss over copper loss. This formula is a real game changer for engineers. It lets them pinpoint the precise output kVA for peak efficiency, ensuring we get the maximum possible performance out of our grid without wasting precious energy. So I want to leave you with something to chew on. How do these strict mathematical limits shape the physical design and the daily, minute-by-minute operation of our massive modern power grids? Understanding these core principles is exactly what makes building a reliable, optimized electrical infrastructure possible. I really hope you found this derivation as fascinating as I do. If you enjoyed this explainer, please make sure to subscribe to Kognito Key, hit that like button, and share this explainer with your friends and colleagues. Thank you so much for learning with me today, and I'll see you next time.